Okay, good afternoon, ladies and gentlemen. I am pleased to be able to say that there is an updated series of slides for you. And the reason that that's happened is that we are dealing with something which is very dynamic at the moment. The recent problems with buildings, not only in the United States, but worldwide, has created a panic in some places, but a lot of activity in others. And particularly in the United States, there is something which is happening very quickly, and I'll be covering some of that. So this is what we're going to talk about this afternoon. The first of all, I'm going to put it into a perspective, the reasons that structures collapse, and then the design philosophy that works towards structural integrity, maintenance considerations, the administrative system for preventing collapses. That's really important at the moment. And then the other side of this is the system shortcomings for preventing collapses. And then we'll look in some detail about where the legal changes in the US are coming, what are current and what have been projected. And they really are current at the moment. And then we'll look at other changes worldwide as well and have a look at a review of the collapses of buildings in the US and worldwide as well, so that we can look at the lessons from the past. And then we'll briefly discuss the problems which are already being created by the legal changes. And additionally, part of the reason for those problems is that there are problems with the assessment of buildings. And then just as an aftertouch, we'll look at other structures, not just buildings, but other structures that collapse. So first of all, why do structures fail? Well, first of all, we need to talk about our nomenclature. First of all, we need to define various things. The first one is the difference between failure and collapse. Collapse is clear. It's if a building or other structure falls down. However, it can fail to perform its function. And if it does, then that's a real failure of the structure. So let's change the name just a little bit and say, why are buildings durable? So we have four things to consider. First of all, their design. Secondly, their maintenance. Thirdly, the impinging forces. And fourthly, the user requirements. So first, let's look at design. That looks at the imposed forces which are opposed by a structure during its lifetime. So there are two things there. You have to look at the forces and understand them, and understand what the suggested lifetime for a building or other structure is going to be. Secondly, the loads must ultimately be transmitted to the foundations. If they're not, then there are loads which will do damage. Thirdly, foundations provide a reactive force. What are we dealing with here? It's Newton's first law of motion. All actions have an equal and opposite reaction. Secondly, maintenance. What we actually want is that if a structure is put up and it's a good construction, then you want to maintain the current integrity right the way through its usable life. And to do that, you must make sure that maintenance addresses those original assumptions and does whatever's necessary to keep that structure close to those original assumptions. Thirdly, and it's a big issue these days, the impinging forces. The assumption is that they're not going to get larger. Well, at the moment, we're dealing with things like climate change, So we're expecting them to get larger. Sometimes the forces, when we're designing, we actually assess what those forces might be in years to come. And so we make adjustments in the design, in the codes and the standards, which go to the designers. If the buildings were designed a long time ago, then they may have been designed to a code which assumed that everything was going to be exactly the same. And that creates a problem for us. The next one is joined to that last problem, and that is that the user requirements. If the user requirements change, they may change the structure itself. We may, for instance, as people are talking about these days, have a building which is an office building, and we no longer have a very large population that uses that office. And we have a problem with housing. So why not use the offices as houses? Well, they're designed differently. So the requirements have to be changed somewhat. For instance, a very simple example is that in an office building, the bathrooms are off in a place which is okay for everybody. But if there are a lot of apartments, then you want a lot of bathrooms in the structure. This has to be done for everybody. And the principle that we're dealing here is imposed forces are variable and they do not get larger. What we often assume is salt, same as last time. We expect that whatever we're familiar with from yesterday, last year, last decade will not change. It's no longer true. And so that presents another type of problem for us. So why are they durable? We have to, in the design, talk about imposed forces and decide what level of risk we are prepared to accept. So the acceptability of risk is assessed by an experienced committee, which is drawn together, a code committee. And it actually has to assess what the community will accept. Well, I've sat on code committees in Asia, Australia, and advised people in the United States, Brazil, and Europe. And I can tell you that they do not go out from these code committees to the community and ask what community will accept as a risk which is acceptable. So the basic standard is that the code committee says, okay, we will take the once in 50-year event or whatever, and that the community will like that. I'll come back to that in a minute because that's problematic. So what is the process for incorporating new information? Well, as it comes along, it's incorporated into standards which back up the codes. So how often does that happen? Normally speaking, if it's really quick, it'll take 2 or 3 years. In the United States, the last iteration was from 2016 to 2022 with the standards that back up the codes. So we have some questions here. Is the committee experienced? Is the information fed to the committee up to date? And is the risk acceptable to the community? They're all problematic. So why do buildings collapse? First of all, the impinging forces are beyond the building's capacity. The forces are larger than those assumed to present an acceptable risk. Acceptable risk. Now we've got a random process that we're dealing with, and so we may design to the once in 50-year event, but we may have the once in 5,000-year event. Has to happen sometime. It could happen now. So what do we do as a committee? We say, well, the force was larger, but it's a random event and you were just unlucky. Communities don't tend to accept that. So what committees do is to just have a little bit of safety factor in there. Additionally, when it goes to a designer, they in turn put a little bit of safety factor on there. Generally speaking, you have structures which are well above what the code actually specifies. Now, if you read the title, if you don't read anything else, read the title, because the title says the minimum loads which are acceptable for existing structures. So in other words, minimum. People are allowed to add confidence factors onto the way they design and the way they build and the way the code committee as well decides on what will be put into a standard or a code. And then we have the problem of maintenance. It can be performed not effectively. People can take shortcuts. It may be performed not in a timely manner. But the big thing is that degradation happens all the time. Buildings do. If you do nothing to them, eventually they will fall down. So there's aging of materials, and it can be that materials are not identified, that they degrade without being able to see them. And then this aspect of change of usage, that is, load paths may change. We may actually change a building from being an office to residential, and as a factor, we put in new shear walls, new partitions, and that automatically changes the load paths of a building. So if you are changing usage, you've actually got to check and see whether the expected lateral forces on the structure actually allow the load path to transfer the horizontal load into the foundation. Additionally, sometimes we get parts of a building which are removed for aesthetic reasons or whatever. That should be covered, but it's not always. So then, modes of failure. What is it that actually causes a failure of a structure? Mode of failure develops if the structure is no longer capable of performing as intended. Okay, so that means that we've got some part of the structure which is trying to be independent. Now we're talking about failure here because if part of a structure is, for instance, a floor, and that is bouncing up and down too much for people to be comfortable, then that is a failure. It's not a collapse. So here we go on to something which is incredibly important in this whole issue of our, our buildings durable. The next thing is human response, because human response is the most complex type of failure. And I'll tell you something more about that in just a moment. There's also physically elements can no longer take the intended loads and paths of a structure, begin to act independently. Well, just because they're acting independently does not necessarily mean that you have a collapse. Not very comfortable to be able to look at it though. Vibrations 101. Humans and their sensitivity to vibrations. Humans are very sensitive to vibration. In general terms, we have this scale. Number one is vibrations felt by humans, the most sensitive ones. And that is a vibration of 0.007 inches per second. Now, if we base on that, so we say this is times one. Level 2 is that people become uncomfortable. That's times 10. Level 3, people become highly distressed about the vibration at 0.67 inches per second, which is approximately 100 times the vibration threshold that the most sensitive people can feel. And then level 4, we then move into what happens to a structure. Level 4 involves light cracking of non-structural elements of a structure. And there we have a limit which is approximately 5 inches per second. It's more complicated because it's frequency dependent, but that's 745 times larger than the most sensitive people just feeling a vibration. Level 5 is damage to non-structural elements, and that is 10 inches per second, which is nearly 1,500 times the threshold for human beings. Level 6, human panic and structural failure. That doesn't mean collapse of a building. It doesn't necessarily fall down if there is structural failure going on. But that's 2,500 times greater than the threshold of perception to human beings. And then level 7, the destruction of the structure. It all falls down 30 inches per second, nearly 4,500 times the threshold of perception. But there's a corollary to this. It's frequency dependent. So in other words, this vibration of inches per second at 1 cycle per second or 100 cycles per second actually has a different effect on the structure. Putting that into a graph, what we have here is one which says here's human response, that's the threshold, discomfort, distress, light cracks, the initiation of damage to non-structural elements, structural failure, and then structural complete collapse included in there. So the conclusions. The controlling system does not respond quickly to the physical requirements. We can't choose change codes very quickly. We can't change the requirements to a change of use of a structure. 2, the inspection process for structures is currently unsatisfactory. So we have old approaches to having a look and seeing whether there is structural integrity. That's why the United States has a problem at the moment. And we'll talk more about that in just a moment. 3, codes and standards do not take into account changes to the environment. 4, legislation is less concerned with occupant safety than with political expediency. I'll come back to that in a moment. Item 5, the lessons of history are largely ignored, and there are lots of them. If we were to look at what worked and what didn't work, given the circumstances they worked in, then we would do much better than we are doing. However, there's an aspect to this. We now have a new technology, and it gives us a false sense of security. I don't know if you've heard about people talking about digital twins. Essentially, what this says is that it is now possible to make a mathematical model of a structure that is so good that effectively the real structure and the mathematical model are twins. Not true. If you're sitting there in front of a mathematical model and you decide what to put in that structure, you make decisions. So your decisions include, do we include windows? Do we include non-structural panels? Well, the problem for you is that they have an effect. The building doesn't know that the non-structural parts are not supposed to play a part in the way the structure behaves. So if we actually measure what goes in a structure and we compare it with a mathematical model, we often find 100, 200% differences between the real response and the mathematical model. So what you need to do is calibrate your mathematical models. And then the last one, lessons of history. Older styles of building are disregarded just because they're old. There are things still to be learned from them, though. So we've got some basic questions to be addressed. The first one is, what exactly is a force? Second is, how do we measure it? Thirdly, how do we characterize winds, earthquakes, fire, and flood forces? How often do large events occur? And how do we address structural integrity? So here we go. What is a force? It's any action that tends to maintain or alter the motion of a body or to distort it. That actually is another way of actually quoting Newton's second law of motion. What's an action? Wind. The force is created by differences of pressure in the atmosphere, and they in turn act on structure. So the action here on the left, we have a boundary layer of the wind generally. So we have friction with the ground, which slows the wind down. And then this increases with increasing height until it reaches what's called the gradient height. The gradient height is a height at which effectively you've got a constant wind speed up to about 2 kilometers. Secondly, we have earthquake excitation. Now this occurs through the ground. Excuse me. And we have two types of motion. The first, the upper diagram there, is that we have a ground motion. If you look at any particular point there, just concentrate on it for a moment, and you'll actually see that it goes backwards and forwards. Doesn't move, but you have waves nevertheless going through the ground. These are the primary waves, and they arrive first when the earthquake occurs. The lower diagram actually shows secondary waves. Now these also are complete waves. Again, if you look at any one of those dots, you will find that they are just going up and down in this case. But again, if you're on the surface, you see a waveform. The third on the right there is we have water forces. Now these are both static and dynamic, and I'll say only a little bit about these later on. Basically, we have reservoirs creating a force on structures. We design all the time. But if we have floods, we have the same process occurring. And there we have the largest forces at ground level. This applies not only to floods, but also to rising sea level. So there we've got a basic quasi-static type of response. In wind and in earthquakes, we have dynamic actions on the structure. And what we have here, I've mentioned it a couple of times now. We have Newton's second law of motion, that is force equals mass times acceleration. D to x by dt squared is acceleration. And if we have a complete equation, single degree of freedom equation, then what we have is that the mass times the acceleration plus the stiffness times the displacement plus, and this term creates all sorts of problems for us, and that is damping times velocity is then equal to the force. We have static or dynamic. So in other words, we can have displacement is the force times, and then there's some function, mathematical function, which actually is a representation of the structure. The force action has two parts here. We have statics, which occurs ostensibly at zero frequency. Nothing occurs at zero frequency, so we assume that it does, and we get approximations to the static response. And then we have the dynamic response, which is a resonance condition of a structure. There is a multiplication factor if the structure is behaving in its resonance condition. So in other words, we can take statics, we can take this same equation, and we can take the equations for dynamics and statics as being one and both of the same part. All it says is that if the frequency is zero, then we have the static equation, and if the frequency is the resonance frequency, we have the dynamics. So we can use dynamics to find out what we're used to by converting dynamics into statics. By doing that, what we're actually saying is that we can make a measurement of how the building behaves under what we use for design originally, which is basically a static approach, by measuring the dynamics. And I'll come back to that as well. And here it is. This is a mathematical representation of a structure. Very simplified. So in fact, what we do is we put together an equation which represents the force acting on a story of the building. And we say mass times acceleration plus stiffness plus displacement minus, and then we've got the representation of the next force there, and that's F1 and so on, F1, F2. You see what's missing? Damping is not in those equations. That's how we do design, which means what we actually have to do is a quasi-static type of approach. All of the finite element models actually assume quasi-static, and then they add in damping after the case. There's a problem with doing that, and that is that damping is a non-dimensional parameter. That creates all sorts of problems to us. Okay, so how do we measure? Once again, Newton's second law of motion, force equals mass times acceleration. All we do then is have a seismic mass, which is allowed to try to move under excitation from seismic or wind excitation. So it's attached to a structure. We have coils or something like that that measure whether that mass is trying to move, and we then feed something in to make that mass stay still. And this, the force that's necessary to stabilize that mass, is proportional to the acceleration. So this is quite a useful way of measuring motion. How do we characterize forces? Quite difficult, actually. The first thing is that we obtain a record of large force events and their magnitudes. Now, if you think about that for a moment, you will see that doing that for wind excitation is much easier than for earthquakes. Why? Because earthquakes generally occur less often than do winds. In fact, winds are occurring every day. They may be quite small, but there they are. So what we have inside our basic standard that backs up our codes of practice is for earthquakes, the intensity of earthquake that gives a 1% chance of collapse in a 50-year period. For winds, we measure a 3-second gust that will occur on average at least once in a 50-year interval. Whoa, now there's something. We draw these, they're called isotachs, like a tachometer. This shows you equal lines of wind speed. Why do we choose 3-second gust actually at 10 meters height? Because the instruments that we used to use are rotating cup anemometers, and they had a 3-second time constant to them. In the old days, we used to measure for a very long time, so we didn't have the problem with the rotating cups speeding up and slowing down. If we measured over an hour, then we were okay. The wind stabilized, and now in the United States, people refer to that as a sustained wind speed. Mean wind speed, and I'll show you why in just a moment, is much better to use as a 1-hour wind speed. 50 years? Why, I'll show you that in just a minute. Why 10 meters? I've already told you, because there is friction with the ground up to a certain height. At 10 meters, we have a compromise between being able to have a tower tall enough to be able to erect it easily and not tall enough to have a problem with trying to estimate what the gradient wind speed is. So why 50 years? I'll go into detail in a minute. Next, though, the wind doesn't blow from the same direction all the time. So why? Why have we got isotachs here? And so we've got the basic wind speed that we use for design. In practice, in design, we use a wind rosette to show what the likelihood is of a wind occurring from all directions of the compass as well in quadrant intervals. So we produce a map for different geographical areas of equal probability of occurrence. For sparse data, only a few years of data, what we do is there is an estimator of what the wind speed for 50 years is. And for earthquakes, it's even more important, although it's not in common usage as yet. Blue sounds actually means the best linear unbiased estimator. Blue, Lieblein blue. And so if you're dealing with floods or earthquakes, it becomes extremely important. In fact, it's being used for the flooding risk in Sydney, Australia, and it ought to be used in a lot of other places as well. We can use classical statistics so long as we've got enough data. We can do that for wind. We do it for earthquakes, but the confidence interval is quite big. These are earthquake spectra, and this is an instantaneous one here. And this is what we put into codes of practice. We smooth it out and say design to that based on the ground type. And here we, seismic engineers tend to use the period. The period is 1 upon the frequency, as simple as that. For wind, then we have something, and this diagram was produced in Brooklyn, New York. What we have is the micrometeorological area here. We have a spectral gap, and then we have the macrometeorological area. Micrometeorological area we deal with for the design of structures. This from about one cycle every thousand, every second is then moves up in a minus 5/3 power law to a peak of one cycle every 40 seconds. Then this spectrum of the force falls off as the time increases, so that we have the spectral gap. And that's why the mean hourly wind speed is very, very useful. And that occurs here in this area. If you use the 3-second gust, then you've got this minus 5/3 power law to deal with. So that's why I say to you, I prefer using the mean hourly wind speed. The sustained gust, which appears in USU standards, doesn't actually tell you how long you've got to average it for. We have two interesting things here. Semi-diurnal, which means we get the day-night influence on structures, and then here we have the peak at 4 days return period. So, in other words, what that says is that at any point on the Earth's surface, the norm is that it takes 4 days to pass that point. Most likely is what it takes. So, in other words, if you're asked what the weather is going to be like tomorrow, until we had better ways of determining the weather, it was always better to say same as last time. And that was because you stood a 50% chance of being right. Now, how often do extreme events happen? On the right here is a diagram showing 5,000 years of Earth's history, assuming salt. It doesn't change. The characteristics don't change. And we have once in 50-year events represented by red dots. So in any 50-year period, because this is a random process, you may have 1 or 2 or 3 50-year events. You may have 4 even 50-year events, or you may have 0. You may have 0 for 150 years. That doesn't change the statistics at all. It just creates a problem because we cannot wait around for 150 years to be able to look at our data. Our best data sets are less than 100 years old, which is why Lieblein has been used on occasion. Now let's look at what the probability of occurrence in any particular time is. So if we have an equation here, P equals 1 minus 1 upon S to the power n. S is the return period, P is the probability, and n is the number of years. So you can put these values into that equation and you can say for 1 year, the probability of occurrence is 2%, 1 upon 50. So that's fine. That most people don't go beyond this. And they seem to think if the 50-year button, the 50-year wind, sorry, let me rephrase that. Once 50 years has gone by, then the once in 50-year event will happen. It's not true. There is a 2% chance of it happening. If you put those values into back into that equation, and we take a 5-year period, the probability of occurrence is 9.6%. 10 years, it's 18%. 20 years, it's 33%. 50 years, it's only 63%. So if you look at this diagram and you count the number of little buckets that don't have a 50-year event in, you'll see that there are 63 of them. 100 years, 86%, 150 years, 95%, 200 years, 98%, which is why on the Australian Wind Loading Committee, we actually raised the return period. We called it a 50-year event still, but instead of changing, instead of describing that as having a 63% chance of occurrence, we raised it way up to a higher percentage. So we got something like a 5,000-year return period. Just being cautious. So now what about design? I've already identified for you that design itself is a possible problem for structural integrity. So the design process, what do? We choose an acceptable risk. Well, the committee told us 2% chance per year is common. Calculate the design event which is associated with this risk. So you want to know the wind speed, or you want to know the earthquake intensity, or you want to know the flood probability. How many floods do you know to be able to put those data together? Thirdly, assemble the data about the design event for the chosen risk, for example, the 50-year wind, and then go ahead and design your building. You will design it on the basis that you are designing the structure and not the non-structural parts. If you're really good at what you do, you'll include those non-structural parts in with very low stiffness, and you'll see what the response is with that. And then the designer needs to model their structure, test the model for the design event. Test the model. How do you do that? Well, you can do it mathematically, but digital twins are a bit problematic. Testing a model on a shake table or something like that, there's a problem with shake tables because, as I signaled to you before, damping is a problem. You cannot easily represent damping in a model. That's because damping is nonlinear and it's non-dimensional as well. So that means that you can only do it if you have a one-to-one scale model. That's awfully expensive to build and pretty useless as well. If you're going to build a one-to-one model, you might just as well build it out in the field. And if you're building it out in the field, well, why not test it as well? So with these things that we're interested in for the design process, neither the code committee nor the designer has all the information that they need. Now, I'm moving on now to what about structural integrity? How do we actually turn this around and say, okay, it's not acceptable to us to have buildings falling down. So what do? Well, first of all, we decide what structural integrity is. So the first element is that the techniques are defined and have been used to establish codes. I say the codes, but in practice, they've been used in various different codes in different places. The current US code, the International Building Code, relies on some tests done in the United Kingdom at a time when there were structures being blown down by the wind and terrorism was a problem which caused something called a progressive collapse. That test on Ronan Point is quoted in the local most recent code of practice in the United States. That particular building was tested before it was then deemed not to be okay. I was the person who led the tests of that structure. Secondly, the codes actually allow for testing of structures. How does that happen? Well, I'll go into some detail later on, but essentially, person who's looking at a structure, a building official says, I don't like that, he can actually, he or she can actually decide that a test must be conducted. Currently, engineers cannot verify structural integrity as required without measurement. Now, when we're talking about measurement, we consider what we did in a laboratory, but that gives us a, a view of how things are, and it's not actually as accurate as we need. Going into detail, structural integrity. We have limit states. US doesn't have limit states. Europe does. So there are different limit states for structural integrity. Additionally, the definition has changed. So, as I say, ASCE 7 actually quotes Ronan Point. Secondly, we need to have the ability of the structure being able to carry imposed loads without distress. The imposed loads are those expected in the design process, and they are risk-based. Distress is a function of the type of loading. Essentially, there are three types. First, human comfort. We've already seen humans are the most sensitive to vibration, and earthquakes or wind will cause a vibration of the structure. Secondly, we move into the elastic area, the elastic range of a structure's behavior. So if we're in that, we have a structural integrity limit state, excuse me, which says the structure must not exit that limit state. So it must behave inside the linear elastic area. Thirdly, we have collapse avoidance, and that applies to seismic engineering, that we do not want a structure to fall down under an earthquake. What we do is we avoid that collapse. So let's look at how we actually achieve this. And if we go back to system theory, then we actually have, first of all, the force acts on our system, and the system is the building. And we have the output response. So we have a goal, which is safety, and we have feedback. Perhaps at the moment, our feedback is not particularly good. So we don't know what the response to forces actually is unless we measure the response of entire buildings. So system theory says unless we have this feedback loop in which we are feeding back our measurement of the response of a structure back to the input here, we don't know whether they've met their design intent or not, or whether they've lost capacity. So there is a possibility of measuring the performance, and there is a performance approach to assessing a structure. That has been used in some countries around the world. At the moment, only a little in the United States, and not widely used, although it's coming. Firstly, what you do is measure the performance at as early time as possible, so you have a baseline. Secondly, compare the performance with that assumed in the design. In other words, you're looking for displacement per unit force there. After an event, you measure the performance again and see if there were differences. Compare the performance with the baseline values and compare with code requirements. Systems approach actually tells us a number of other things as well. We actually look at the structure as a system, and the design and build process is also a system. So what we have here is actually a diagram which shows you how a system actually works. Three parts of the structural design process. What we want from the design, and then a decision-making interface. We have energy, which is the design implementation. We have performance measurements. We analyze it and feedback here. Now, this is actually the decision-making interface is codes, universal intelligence, company internal knowledge, specialist advice from the code committee. So we actually compare what we wanted with what we've actually got. If you do this, then you have a stable system. If you take out this, the analysis and feedback, you do not have a stable system. Without this occurring, then the whole system is unstable, and sooner or later if you're lucky, there will be a problem with this whole system. So analysis and feedback of the way buildings actually behave is crucial to the stability of this system. So traditionally, feedback in codes of committee has come from big league government research. That tends not to be used these days because it costs money. It costs a lot of money as well. Code committees gather information and formalize it. So they sit and argue and talk about what the code ought actually to say. Normally speaking, that is. When we have a problem, we act more quickly. And with, as I've said before, with the electronic revolution, we actually come to a situation where feedback is possible and has become an economic possibility. That is, you can collect and analyze data coming from a structure very quickly, compare with what you expected, what the code says, again, very quickly. Maintenance considerations. There is a standard, ASC 1199 standard, a guideline for structural condition assessment of existing buildings. Now, this lists methods for performing a load test, determining the dynamic response of a structure is an improved method. So in other words, this standard by ASCE and SEI actually says performing a load test on a structure is already okay. If somebody is looking at a structure and thinks there's a problem, they just need to say ASCE 1199 allows me to say do a load test. Here are the 16 different methods of in situ testing. You'll see that all but 3 of them are actually local. They are checking what the characteristics, what the parameters of individual elements in a structure are. So things like ground penetrating radar, thermography, fiber optics, you can use that on individual elements of a structure. Dynamic analysis, you can use that on a full structure, and you can make in situ strength measurements like that as well, although that's much more expensive. Of course, we're brought up to laboratories, and we use Hooke's law, which says displacement equals force upon stiffness. We do laboratory experiments, well controlled, and we're used to machines which will allow us to do that. So when we come to testing structures, we're actually conditioned by what we did in laboratories. We forget that statics, and these are quasi-static tests, are just one element of the entire mathematical devolution of the problem. In other words, dynamics will also tell you what the force per unit stiffness is, or force per unit displacement will give you the stiffness of a structure. So it's possible to do, but we're conditioned by what we did in laboratories. Our students should get out and do full-scale experiments on structures. So the administrative condition. What do we do? So we've got a problem and we have a number of interested parties. What's their response? First of all, legislators. We've had a building fall down. We have to do something, and quickly. Design engineers. Just tell us what to do and we'll follow the code. Building inspectors. You're giving us an impossible job to do. I actually gave a presentation to building inspectors in Florida and said to them, there are certain things that you cannot possibly do, possibly do. And there was shaking of heads right the way through the audience. There were 50 people there, probably about 30 of them were building inspectors, and they agreed. You cannot get to every single point, every single element inside a building to look at it. Move on then. Financiers. Well, don't make it cost too much. Insurers. Yeah, this is going to cost more. Owners. We can't afford it. That's a real problem. Structural risk assessors. Stop messing about. There's a simple, cheap, quick method to assess structural integrity. And I'll tell you more about that later. So there are two things that must happen legislatively. The identification of structural defects must be feasible, physically and financially. There must be sufficient funding to enable the repair of degrading buildings, and these items must be mandated. Codes of practice call references as standards. Standards are produced by experts. Standards call references to published papers in peer-reviewed journals. And ASCE SEI has committees considering changes to ASCE SEI 1199. Now, in practice, I'm not sure where that's going. I'm a member of this committee, and it's ASCE SEI 1128. So now, I've said to you, Ronan Point was a watershed in the past. So let's look in a little bit more detail here. We had a gas explosion up on the 22nd floor, and the explosion took out the apartment above. That fell, and the load was too big for everything below, and so there was what we called a progressive collapse. Sometimes it's called a disproportionate collapse. This happened in 1968. The building was rebuilt and strengthened. So in 1984, I led the team which had a look at the new building, and we found that it was coming apart at the seams. This is because it was a system-built structure, large panel construction. It was called a Larsen-Nielsen system, and in the UK, they allowed it to be used for these taller buildings. In the US, they were limited to 5 stories. I'm not sure that 5 stories is enough. Anyway, the one person dropped a piece of paper one day, and the piece of paper dropped between a floor and a wall of her apartment and went to the apartment below. So immediately there was panic. I was working with the UK government at the time, and we went in and used a vibrator system. And this is actually a picture of it, together with a very early version of the most precise accelerometers in the world. And we looked at the building and measured the the link between individual panels and the response of the whole building. What we found was that despite the building coming apart at the seams, it actually had a risk ratio which was not different from what the design said. It had a weakness. So we produced a report, and the report said you must make sure that a building can work and transfer loads to the basement through multiple directions, through multiple load paths. Additionally, you should not have gas in a building, so that was banned. However, what it resulted in was a result of us doing an experiment in our laboratory. And the laboratory was that of building a 1/4 scale of Ronan point. And to do that, this is what signifies one of the problems that you've got here. If you have 1/4 scale, then the mass that you're using in the building actually decreases by not 1/4, but 1/4 cubed. So you got to put extra masses in the structure. Now this was to the new code of practice that we produced because of Ronan Point's problem, and we did various things to the structure, including simulating a gas explosion in the building, and we got this, a progressive collapse, just like Ronan Point. Now, this is with new codes of practice, new standards, saying that in practice, we actually have to do something different. I could say something about the reports, but I'm not allowed to still. It's still secret. The Royal Society. I've talked to you about us using various things. Newton's laws of motion, for instance, Hooke's law. They were original members of the Royal Society. Now, the Royal Society was formed in September 1660. It's the oldest scientific academy which currently exists. And there are some well-known people: Isaac Newton, Albert Einstein, Thomas Young, Robert Hooke, Ben Franklin, Michael Faraday, Charles Darwin, Dirac, Winston Churchill, Stephen Hawking. And we use even today Newton's laws of motion, Young's modulus, and Hooke's law for basically what we do to test structures. So Newton actually produced something really rather good. He introduced formalized logic into the mathematical process of dealing with nature's forces, and said that in that publication, is spread the light of mathematics on a science which up until then had remained in the darkness of conjectures and hypotheses. So all of our current engineering is based on Newton's work with a review of Bertrand Russell in 1901. That's what we use today until we start flying aircraft, flying spacecraft to other planets. So now let's just take a look at what happens in the US. Current and projected changes. So in 2022, we introduced some legal changes, and a number of laws now require a verification of structural integrity. Florida was the first, SB 154, and it's required a verification for structural integrity and transparency. New Jersey, structural integrity of buildings was signed in August 2024. That's New Jersey Law 2760. Virginia, Delaware, California, Indiana, and other states, including New York City, are passing laws. There are rapid changes going on. Freddie Mac and Fannie Mae, excuse me, are selling guides requirements. They have produced selling guide requirements for condominium projects, which include lender expectations for critical repairs and for structural integrity. So legal changes in the US have put all parties on notice. So what is structural integrity? ASCE 722 is good. It says in Chapter 1, Section 1.4, all structures shall be provided with a continuous load path in accordance with the requirements of Section 1.4.1 and shall have a complete lateral forward resisting system with adequate strength to resist the forces indicated, and goes on then to define exactly the sort of things that I've talked to you about. Essentially transferring the load imposed by wind, wave, water, or earthquake to the foundations of the structure. And we have an in situ load test per the IBC and ABC and ASCE 7. So the building official right now is authorized to require an engineering analysis or a load test or both of any construction, whether there's reason to question the safety of the construction for the intended occupancy. So there's a performance requirement in the codes. There was a paradigm shift in 2022, and I'm repeating myself in a little bit there. So Florida Senate Law 154 is the canary in the mine because they moved quickly because of a building collapse. And I'll say more about that in a little while. Inside Senate Law 154 for Florida, they say the legislature finds that maintaining the structural integrity of the building throughout the life of the building, its service life, is of paramount importance in order to ensure that buildings are structurally sound. Performed under the direction of an architect or engineer licensed in the state of Florida for the purpose of testing to life safety, adequacy of the structural components of the building, the general condition of the building as it affects safety of the building, including safety, repair, and replacing of structural components. And then it says, to the extent reasonably possible. Now they actually had something, and this is included in your edition of the um, of the presentation, some information about what happened in Florida, and the ASC 7 committee introduced an effort of investigating and telling people what was necessary. So about what they call milestone inspections. Milestone inspections occur when there is a requirement for a building inspector to take a look. And there's information about where you can find more information on these things. Basically, in the new Florida law, milestone inspections must start when a building reaches 30 years of age. The initial milestone inspection, based on certificate of occupancy issuance date. So if the building reaches 30 years of age before July the 1st, 2022, then by the end of this year, an inspection must be completed. That's a stage 1 inspection. If it first got its occupancy approval between July the 1st, 2022 and December the 31st, 24, then it must have that inspection before the end of next year, 2025. If it got its occupancy approval after December 31st, 2024, then the building may be 30 years of age and it will be tested then, or it will be inspected then, and every 10 years thereafter. And local enforcement agency may require inspections to start at 25 years due to specific local conditions. The inspection responsibility. This is the building inspector, responsible for ensuring compliance. The condominium or cooperative association bears the responsibility for all costs associated with a milestone inspection. Local enforcement agencies have the authority to prescribe timelines and penalties for compliance to ensure adherence to required inspection schedules, and the milestone inspection report must be obtained by condominium or cooperative association, owners of any portion of the building not subject to the condominium or cooperative form of ownership. They have a responsibility as well. So condition rating. The building inspector can say it's good, fair, poor, or significant problems. So good, no substantial deterioration and no dangerous condition is observed. Fair, the indication of substantial deterioration was observed and no dangerous conditions were observed. This does happen on occasions. Poor, there is actual substantial structural deterioration observed and no dangerous condition is observed. Significant, any observation that is an indication of a dangerous condition or actual dangerous condition. And then, if it is dangerous, the inspector can say something must be done immediately within 24 hours, or it's less immediate, maybe within 10 years. So dangerous, that would be any building, structure, or portion thereof that meets any of the conditions described below. Firstly, the building or structure has collapsed, has partially collapsed, has moved off its foundation, or lacks the necessary support of the ground. I would think that would be relatively obvious. Second one, though, is more difficult. There exists a significant risk of collapse, detachment, or dislodgement of any portion, member, appurtenance, or ornamentation of the building or structure under permanent, routine, or frequent loads, under actual loads already in effect, or under wind, rain, flood, or other environmental loads where such loads are imminent. That creates a problem because the building inspector goes in and he has to assess these sorts of things. If he's not sure, then he is allowed to follow anything which is in publication by ASCE SCI, including ASCE SCI 1199. So milestone inspection. What's reasonable? What's possible? What is possible and what is reasonable? Well, what's not reasonable is inspecting every single structural element, because if you read between the lines in the new law, it says you've got to. You can't, but you can assess the holistic behavior of the entire building. So assessing all structural elements, a lot of them are hidden behind cladding, behind all sorts of things. Assessing structural integrity using a visual-only inspection is not possible. Using engineering judgment only. Well, if your judgment is really good, that might help you, but it's not a guarantee that you can assess structural integrity without doing tests. So the law talks about substantial structural deterioration or substantial structural weakness, but these do not include cracking, finishes, peeling, water penetration, sagging, deflections, and misalignments. In other words, these are normal parts of a building. That is, so long as the cracking is not too big. So don't get distracted by the cracks unless they get large enough to provide a problem for structural integrity. There are two phases to the milestone inspection. Phase one is mostly visual, although it could be augmented by tests. Phase two can be destructive or non-destructive. The intention in both phases is to assess that the building is safe for its intended use and structurally sound. Our reports have to address the following: type and manner of the inspection, structural deterioration, if there is substantial structural deterioration, state whether unsafe or dangerous conditions were observed, and recommend any remedial measures or repairs needed. Substantial structural deterioration, what exactly is that? Florida's building code, Senate Law 154, tells you, it spells it out. A reduction of 33% of the lateral load-bearing capacity from the pre-damaged condition, and/or a 25% reduction in the vertical load-bearing capacity. Now, how are you going to assess that without doing a full-scale load test on the structure? The answer is you can't. New Jersey has followed along, although it's a much more streamlined type of law. It was signed in August 2024, this year anyway, January 2024. It provides guidelines for inspection and reserve requirements, and it sets the precedent for other states as well. Because it's streamlined, it's easy to get in and leave the handling of it to somebody else. Engineer and owner requirements and definitions. Appropriate procedures for inspecting, evaluating, and maintaining the structural integrity of residential housing. Primary load-bearing system means the assemblage of structural components, excuse me, within a building comprised of columns, beams, or bracing that by contiguous interconnection form a path by which external and internal forces applied to the building are delivered to the foundation. You see, we're hearing the same thing devolving from the Ronan Point tests, Ronan Point report that occurred in other places. So continued. Determine when the next inspection shall be performed. It doesn't actually say when, but it does say if you use ASCE or other standards, your protocol is okay. Provide guidance or maintaining structural integrity, new or progressive deterioration. The inspector is exempt from liability if they follow ASCE guidelines. Review of collapses of buildings in the US. Now, this is what caused the problem. Here we have the response. If you look at the dates from which these occurred, they are all post the collapse in Florida. It's been followed with Colorado, Connecticut, Delaware, Illinois. There are two parts to the Florida Code. They immediately went in and they've adjusted it slightly in 2025. Oh, it will be in 2025. Hawaii, Illinois, Maryland, New Jersey, New York, it's under discussion, Tennessee and Virginia. Worldwide, the UK and the EU and Australia have things. Now, I've also said here, what have we got? Have we got a structural integrity requirement? That's this column on the right here. Have we got a reserve requirement? In other words, it's always a problem. Sorry, it's possible to have a law which says we must have structural integrity. But if there isn't the money to do what's necessary, then you got a problem. So in Colorado, they don't. They have not ruled that there must be a reserve fund. Additionally, in Hawaii, there is no requirement for a reserve fund, nor in Illinois, where they have had a progressive collapse as well. So here we have Champlain Tower in Florida. 98 people died, $1 million loss. And yet before the collapse, there was deferred maintenance. This was a building in 2015. Funds did not address damage. Repairs in 2018 were estimated at 6 million. Repairs in 2020 were estimated at 15 million. But now it's a lot more expensive to deal with the problem. The repairs weren't started in 2021. The property manager knew of the weakness, and bad advice and decisions led to the collapse. A simple load test on the structure could have identified whether there was a general problem or a localized problem. And then in Iowa, we had a building. This was caused by a winter event called a derecho. The building is 100 years old. 3 people died. 70 families were left homeless. The structure had significant documented deterioration, and it was a strong wind, it's true, but they painted over cracks there. So now let's have a look at worldwide collapses and see what lessons we could actually use. So we've got here a number of big collapses around the world. There is the US government building here brought down by a terrorist. Okay, so we're familiar with that sort of thing. And this is the Colossus of Rhodes, which fell down because of an earthquake. And because it was so large, laid for nearly 1,000 years, not being removed. Ronan Point, I've told you about before, it was a watershed and it told us what was going to happen in our codes of practice. This is Ferrybridge in the UK, where a cooling tower was blown down by a wind, designed to a code there back in the late 1960s. Then we have terrorism, that's the World Trade Center, but ordinary buildings. This is in Japan, and it looks as though it's okay, but it's just come loose at the foundation. So there was actually a foundation problem there. This one is in France, in which there was somebody trying to make changes to his apartment, and the whole structure came down. And here, this one is in the US. So there's for your delectation, you can take a look at this later if you want to, and you'll see that there were quite a lot of large structures which fell down. But look just recently, Champlain wasn't the only one that had a progressive collapse. In Russia, they had a 10-story building which had a gas explosion. It had gas in the building, and a gas explosion caused a progressive collapse. And that was a long time after Ronan Point. So they hadn't learned the lessons. Bangladesh, there was a building used as a factory, and it collapsed. It just became old in 2013. 1,300 people were killed. Uh, and Sampung department store in South Korea, 500 dead. Those are buildings which have just deteriorated over a long time. I've already covered that. Look at some other things that we could learn, though. First one is this is unreinforced masonry. The Pantheon Dome in Rome, sorry, in the yes, in Rome, has no reinforcing in that dome. It's kept up by gravity. So, and it's lasted for over 2,000 years. And then the Segovia Aqueduct, also in Rome, and that is unreinforced masonry, and it's been repaired a number of times, but it's still able to perform its original function. And there at Machu Picchu in South America, unreinforced masonry once again. And by careful stone masonry, it stood for, well, 600 years. Now, what about problems created by these legal changes that we are rushing into effect? So, Florida, first of all, a financial reserve must cover anticipated remedial work. Condominiums may be unable to set aside funds necessary. Owners may be required to pay for part maintenance of the entire building. A budget must be established by the end of this year for buildings over 30 years old. The necessary work has to be completed by January 1st, 2027. Insurance costs are rising quickly anyway. So the value of individual units are reducing because of the additional financial constraints. And a lot of the condominiums in Florida are 50 to 60 years old. Now, I did say you have a new update on this presentation, and that's because things have been changing so rapidly. This happened just 2 days ago, and that is that a television company organized a town hall meeting because owners of apartments in a condominium there had estimated, they got an estimate of the work that was necessary with a reserve study already done, that the condominium owner was going to have to pay $3,000 per month to cover the reserve costs, and that all of the people who owned um, uh, units in the condominium. So you can see the television company um, organized it, got a lot of people who were clearly interested. Now the building assessment, I've said you can't expect every structural element or all structural or assess them. You cannot assess the structural integrity with a visual only inspection, and you can't just use engineering judgment. Structural deterioration, structural weakness, and structural distress. Let me move on. I've already covered that. And that, excuse me, just a moment. Okay. So robustness of a structure. The expected characteristics must include the ability to resist the lateral load, absorb impacts due to accidental loading, like in Ronan Point. We tested in our laboratory model not just a gas explosion, but vehicles colliding with the structure. That's another aspect. Another collision with the structure is a flood as well. The ability to tolerate inaccuracies and uncertainties in the design as well, and the ability for the structure to redistribute loads safely. Australia, the UK, and the EU have gone a little bit further in looking at these things. In fact, they have tests for ductility, the ability to carry load while undergoing large deformation. Actually, they have another problem. And that is that the fascia panels of a building have a fire-resisting material which is flammable. And so with the Grenfell Tower, they had a massive, great fire to that structure. A lot of people were killed in that. So number two, stability, the ability of the whole body movement, such as sliding and overturning, to be resisted. Buckling, sudden inability to carry compression loading. In other words, somebody putting a big load on their wall or their floor inside a condominium. Is it reasonable? Will it buckle under the compression loading? And then load paths, the ways the forces are transferred from one element to another until they reach ground anchoring points. In other words, are there multiple directions that this transfer can occur? Redundancy, the availability of multiple load paths. Impact resistance, joint strengths. You've had a problem in the United States of the ability of joints to maintain their connection to transfer forces from one structural member to another. And again, I would go back to this digital twin thing. One of the decisions you make when you're creating a mathematical model is, what is the connection between two elements? Will I assume it's encastre, or will I assume that it's sliding about? It's a decision, and the designer can actually make a decision one way or another. All of these are influenced by the progressive collapse of Ronan Point. There are other structures and collapses which occurred, bridges, dams, chimneys, for instance. And in fact, we have aerodynamic instabilities, Tacoma Narrows, which I'm sure you'll be aware of, 1940 there. Volgograd, though, did not learn from Tacoma Narrows sufficiently to avoid that type of instability. Now, the Tay Bridge disaster was an incredible one. A large number of people were killed. They had used a quasi-static load back then, 1879. They used 10 pounds per square foot as the loading. And speeding trains going north in that photograph. The design was compromised by cost. The wind gust probably reached only 65 miles per hour, and the bridge collapsed with a train on top of it. However, the latest research suggests that the reason for the collapse was fatigue of the members. A researcher got hold of some of the elements of the collapsed bridge, took it away, and analyzed it 100 years after the event, and found fatigue cracking occurring. And by the way, the designer at the time of building the Tay Bridge was the Astronomer Royal in the United Kingdom. And because the bridge fell down, so many people were killed, he was absolutely pilloried. He was given the sack from his job, and he spent his last few years in poverty and hated by everybody. 100 years later, it turned out it wasn't his fault at all. However, we changed the codes of practice. What happened was, and this is the thing that changes. There was a Tay Bridge disaster in 1879. In the 1940s, Tacoma Narrows. In the 1950s, we still had prescriptive codes of practice. In other words, we simply said, we'll take a certain wind, convert that to a static load, and then we will tell you what it should be, and we will tell you how you should build your building, what size elements should be, how far apart columns should be, that sort of thing. Late 1980s, we went to the early stages of performance. But what we did as a first stage was to say, okay, we know that the loads are random forces and we will deal with those. We will make them not prescriptive anymore, but there is a risk depending on the different types of structure that you have. So in other words, you will only allow a smaller risk for the structures which are important to lots of people or are places where you all gather and hide after an event. So immediately afterwards, with the Tacoma Narrows, we raised from 10 pounds per square foot to 30 pounds per square foot, and then included dynamic effects in with the work of Alan Davenport, who was British but worked most of his life in Canada. 1950 to 2000, the codes were prescriptive, and 1989 onwards, we had performance assessment goals, which were introduced, including in other places in the United States as well. So from 2000 to 2022, we had risk and performance progression. We had a lot of lessons to learn from what the Tay Bridge taught us. Code requirement was immediately changed to £15 a square foot, went up with Tacoma Narrows to £30 per square foot, but it was still missing the point because the Tacoma Narrows was not a quasi-static failure. So in other words, unless you take into account the dynamic part, you're never going to produce something which will avoid that aerodynamic instability. So in other words, next, the quasi-static only load is changed to include dynamic. Pity that not all designers actually understand that. Frequency is easy to measure, even at high amplitude. Seismic engineers do measure frequency and use it to see if there's changes there. But we moved on further because we needed to know about frequency and damping. Ellis and Cantini showed a frequency correlation with structural dimensions. So in other words, you can look at the height of a building and you can show what the expected natural frequency of sway is. As a matter of fact, I shared an office with Brian Ellis for a long time, and Reto Cantini and I were on Eurocodes together. The most difficult thing was damping because it's nonlinear. Seismic engineers really wanted to know, but they said, you cannot do it. It's too complicated. Well, in the 1980s, I introduced something based on what NASA had done to look at the nonlinear response of nonlinear damping characteristics of a building. And as a result, it was able to put together the frequency expectation and the damping expectation. And by that, we can actually look at the displacement per unit force. We can do that in the linear elastic zone, but it's useful. And I'll show you in a moment exactly why. Ron Mays did some experiments on motion of a tall building, which was going to be demolished anyway, beyond the elastic limit. And that is the only one in the world that has ever been conducted. Kit Scruton developed equations to identify aerodynamic instabilities. And then we had Alan Davenport and Bob Scanlon working on dynamic wind forces. So there's a list of people who've made fundamental contributions to the way that codes are going. And then, this is an interesting one, the Brooklyn Bridge in Manhattan. It's a hybrid cable-stayed bridge. And at the time of completion, it was the longest in the world. It was opened in 1883, 4 years after the Tay Bridge collapse. Has masonry towers, anchors on land near the river. Construction started in 1870, renovations in the 1950s, 1980s, and 2010s. However, there's something very interesting here as well, because they to build these towers, they put caissons in to keep the water back and went down inside those caissons to do the structural work. Unfortunately, to keep the water out, they had to have high pressure. And a lot of people, including the original designer, Warren, his name, got the bends from high pressure. They didn't understand what that caused to human beings. In those days, women were not able to get into positions of doing that sort of work, but the original project manager was married to Emily Warren Roebling, and she knew everything about what was going on and was able to finish the project off and she continued after doing the Brooklyn Bridge to take exams to become eventually, after a long, long fight, a chartered civil engineer as well. She was a real person who led by example. So then there are design errors, and here are a couple of pictures of errors which have occurred on bridges, scour in bridges as well. The Ferry Bridge cooling towers in 1965, with a wind which was coming from this direction. Why did those three towers fall down? Aerodynamic, because of a Venturi effect in which the wind was channeled between the towers upstream and created a larger force on the ones downstream. Why didn't this one fall down? Nobody knows for sure, except to say if anything was going to fail next, it was probably that one. The interesting thing was that one person filmed what was going on, and he actually saw cooling towers, which were, in his words, doing a belly dance. So he could see there was a problem, went home and got his picture, his camera, and took a picture of a tower just falling down, one that I showed you before. I did some work on Ferrybridge cooling towers and these chimneys as well, and talked to somebody who was um, at the site for a very long time and said, can't understand it. The cooling towers fell down despite the fact they were supposed to be 8 inches thick. And he said they weren't 8 inches thick, they were 5 inches thick. I said, no, no, the design said 8 inches thick. He said, I built them, they were 5 inches thick. So there was a construction problem. Nevertheless, we actually design our cooling towers very different from Ferrybridge these days. Dams. Sometimes there is substandard construction materials or techniques. Gleno Dam, spillway error design, the Glen Canyon Dam, and Woolnock Grove Grand Dam. Lowering of the crest height actually reduces spillway flow, and South Fork Dam in United States, that fell down as a result of that. You wouldn't think it would be that way down. Geological instability caused by changes to water levels. In fact, I did some work on dams in Scotland, and a lot of earthquakes occurred underneath the reservoir where the water was actually lubricating the slip zones underneath. Landslides causing overtopping of a dam, an extreme inflow, and the Shakador Dam failed as a result. Errors in human computer or computer design, internal erosion or piping which doesn't work, especially in earthen dams, which caused the Teton Dam failure, and then earthquake and climate change effects, which we're seeing at the moment, where large downflows of water are actually causing some problems for dams which don't like water levels above their crest level. And there's the Teton Dam, in which there was a failure of the structure, and you can see the reservoir completely falling. This started with a little track through the dam, which caused a hole in the material. The water started pouring out, and gradually, as you can see, There's a tremendous force there. And of course, imagine the downstream population will have a severe flood occurring as a result. I mentioned doing a number of different dams, their problems. That one is Emerson Dam in Switzerland, which I shook. Wimbledon, I shook all of these. Wimbleball Dam in Wales, now which is a buttress dam. Every single buttress is considered to be a separate structure, but it's not if the reservoir level is high, and then these buttresses tend to operate as a single entity. When the reservoir level goes down, they all operate individually. And of course, they're different heights, so they all have different frequencies. Now, this one here, Contra Dam, is in Switzerland. We had a big storm. We had gone in, set up our vibrators on the dam, and got struck by lightning. In fact, the lightning strike was just off the edge of the dam. But nevertheless, it went into our wires, which are along the crest, and caused all sorts of damage to our equipment. The reservoir level rose 10 feet overnight, and you can see that there was an overflow here. They were worried about this overflow going right the way over the top. Now, I, at the time, had decided it was better to be off the dam, but only after being on that dam and feeling the intense vibrations of it and thinking it's not a good idea to be in this place. I want to be on firmer territory. So I and my team moved off as well. So we did other dams. Earthen dams behave monolithically. Like it or not, they do actually. Their modes of vibration, they sway, they vibrate in the same way that that concrete dams do. But being earthen, they actually consider that the surrounding countryside is always part of them. So there is not encastre applying at the edge of a dam, but the surrounding countryside also shakes around. So we put vibrators on these entities, these dams, and shook them, and actually had quite a big argument about making measurements that we could only stop at the end of the dam, whereas in practice, no, we needed to measure the surrounding countryside as well. Isn't nature wonderful? So we've done the same sort of process in Northern California as well. There's a dam here, and this is 87 years old. It's near an active earthquake form fault, about 6 miles away, and it was subject to freeze thaw. So we did an analysis, a load test, effectively without vibrators, just using the upstream movement of air acting on the dam itself, using a structural cardiograph, solar power to drive everything because there was no electricity supply. We had to get it from the sun, and we used satellite communications to get our accelerometer's output through the internet to be able to look in detail. We analyzed that dam, and by analyzing a lot of modes of vibration of the dam, we're able to say there is a crack in a certain position in the dam. So one of the project managers went to have a look and asked me where. So I told him where I thought it was, and he said, quite right. It's about 1 inch thick, and it's exactly where you said it would be. In situ testing. So I've told you about the basic equation using Isaac Newton's second law of motion, and having a look to see what the capacity of the structure is. Now, if we take that equation and look at it for the resonance condition, we find that displacement upon force is given by this: damping, frequency squared, the mass of the structure, and pi squared. So you only need to measure these two parameters, damping and frequency. And that way you find displacement per unit force. So you don't need to know the force, you only need to know this ratio. And this ratio actually occurs in something that we always use, which is Hooke's law. And that looks at the displacement per unit force in the linear elastic range. So after you go into the nonlinear zone, then you've got a little bit of a problem because it's no longer linear. However, after the event has gone away, that displacement per unit force changes if there is a problem with the structure. So what you do is you measure this displacement per unit force and you compare it with the expected response, because now, because of Ellis's work and my work, we can actually say what are expected values of frequency and damping. That means that we can look at the risk, we can put it into an equation, and we can look at what the return period is to create something which will take you outside the elastic limit, and you can assess that um, for um, a wind speed or an earthquake. We have frequency of estimation. This is from Brian's work, Brian Ellis's work, that is, of what the best fit of frequency is. 46 upon H in metric units, 150 upon H in where H is in feet. And this is from Reto Cantini for bridges, mainly in Europe, and that depends on the length of the main span. So with both of these, we can actually look at displacement per unit force. I have some other slides which you'll be privy to. You'll be able to have a look at them. Our time is up, so I'm not going to go through these, but you can take a look at what are effectively load tests included on various buildings. This one at West Point, I'll just show you which ones. This is in New Zealand, and we identified something which was hidden from view. They took it to pieces, the town hall in Wellington, New Zealand, and found a broken structural member in there. A building in New York City with the felling of a bridge viaduct just nearby. We looked at that, and this is what I really want to show you, is that we calculate the risk ratio in this particular case where the poor building had had a return period of 12.86 years for a wind that would take it outside the elastic limit before the felling of the bridge. After it, there was some damage, and that reduced to 2.3 years return period. What they did, though, because the area was just warehouse, they said we'll continue using for that, and if it falls down, then okay, we're okay with that. So this load test limits liability. It gives due diligence for having done everything that the new laws in the United States, Florida, New Jersey, and all of the others, Virginia, we've just done a test in as well. So they identify weak buildings, and they say whether the load test tells you that it's okay, generally speaking, holistically, or whether there is, excuse me, a localized problem which needs fixing. So it allows people to prioritize budgets and fix what needs to be fixed. And it assures that work meets the design intent. In other words, commissioning. So you can have quicker reoccupation after something like an earthquake that they had in New Zealand. So these objective measures, and they are objective, you make a measurement, analyze, and have your measurement of displacement per unit force, and it helps assure safety. It compares all structures based on risk, even if you can't see broken members. So it's appropriate use of system theory, and it provides this objective mechanism to improve the building stock. It also works now. We're just finding information about wooden structures. So with a move towards environmentally friendly type of construction, wooden structures become more important, and we find that it works for them as well. You can actually find, and this is from Europe, actually, the blue line is Brian Ellis's 46.H. So wooden structures are actually somewhat stiffer than uh, um, than concrete buildings and steel buildings. However, there is a slight problem with building them and making sure that you maintain that. And there are just the odd ones which have a lower stiffness to them. So, concluding remarks, and these are important. We need to assess the in-service performance of structures. Our legislative procedures need a drastic overhaul. There are various inputs that we need to deal with. Education of engineers needs to include courses on logic, dynamics, wind forces, speed is not a force, and the history of the subject area. And we need to install a good appreciation of statistics in seismic engineering, in which just a small quantity of data can be turned into something usable in codes of practice. So, ladies and gentlemen, thank you very much indeed for your attention. I hope that you've enjoyed this, and if there are any questions, I would be happy to answer them, either now or at some stage in the future. If you want to, you can contact me directly. Thank you very much. Okay, yes, for those of you who want to get um, your quiz, and after this webinar, you complete the quiz, and you can get a certificate of completion, which you can use for continuing professional development. So, Patty Smith, there's a written comment saying, "Thank you for a very informative and interesting presentation." Patty, thank you very much indeed for your kind words. That's very much appreciated. Okay, ladies and gentlemen, if there are no other questions, thank you very much. And at this stage, we are going to call a halt. Thank you very much. Oh, and Brian, thank you very much for your kind words as well. Ladies and gentlemen, goodbye. I hope you have a good rest of the day. Bye for now.